One. So, I have been already introduced. My name is Stefan Wiedmann, and maybe I can have my slides. Hi, hello, my slides. Ich bin am VGA drauf. Und ich. Ja,
Wahrscheinlich hat er jetzt den falschen Bildschirm genommen.
Nein, das ist nicht mein Rechner. Nein. Okay, so while we're waiting until my slides appear somehow, who has seen the incredible talk about hacking the voice over IP phone from Cisco last year, either live or on video? Okay, some of you. When we think about this talk, you know, the Cisco voice over IP phones have an embedded Linux operating system, but they did not only have to deal with the Linux operating system, but also with the firmware of the DSP. So what I want to tell you is that there's not only one system, but there are several systems, several subsystems containing firmware. And yeah, slides would be nice. So we can start without slides, it's no problem. So what are we going to talk about today? Okay, first we will talk about the motivation. Why should we do firmware analysis? And then we need to be able to do it. So we have some prerequisites to bring with us. And then we'll dig deep into the topic. So we will try to look, how can we obtain a firmware? How can we analyze it, and how can we modify it?
We're sorry for the brief hiccup here. We're working on that. It's the second talk. I'm sorry.
Also er zeigt mir hier das nur an, wenn extra. Wir können auch den anderen probieren. Okay, we without slides, it's okay. So let's start with the motivation. Why do we want to do firmware analysis? So when talking to my lawyer, I learned that I had to clean up 90% of my motivation slide, and left is you can do it if you want to gain interoperability. Okay. You can do it if you want to get rid of errors, and the manufacturer does not want to or is not able to. Okay? And one interesting point that is under discussion is, what about forensics? What about taking a look in those thousands of embedded devices in our everyday life? Do they really only do what they are supposed to do? Okay.
Yes, we're still hunting for a video angel to sort this little problem out. We should have one here within a minute. I'm again very sorry. We now have Nick Farr on stage, our certified PowerPoint specialist. It can only take minutes now.
Try to. Okay, maybe we can continue. So I will just tell you something about what are prerequisites you should bring with when starting to analyze. Okay, first, you should have at least a good knowledge of the architecture of embedded systems. That means you should have dealt with peripherals, bus interfaces, and so on. You should be able to read and write assembler. Okay, some might say, hey, I have a very good decompiler, which is absolutely fine. Okay, perfect. If it does work for you, okay. But don't rely on the availability of a decompiler for the architecture you're going to be working on. And especially if you are going to work very low down in the register stuff. And in my opinion, a decompiler output will more confuse you than helping you. You will go to disassemble maybe C runtime libraries optimized to be as small as possible. That can be really hard in a decompiler output. If you want to practice how embedded systems are working, then it might be a good idea to fetch your Arduino or whatever. You write some little C code, maybe handling some hardware stuff, and then you just compile it and take a look what this assembly looks like. Very nice to have is a device reader and programmer, like Galeb, for example. The problem is they are very expensive, but if you think, yeah, we're going to do firmware analysis, it might be a very valuable investment for your hack space. And last but not least, what you need most is time. Time. It may take hours, it may take days and weeks without any progress, so please be patient. Any volunteers to make up some slides here? Okay. I swear, it worked perfectly okay with my external monitor, I swear. Yes? Das kann gut sein, okay. So I'll have to fetch my USB stick. Wait a moment. No problem. We are flexible. ODP.
So, is there anyone who knows its way around the computer around here? Yeah. While we figure that out, that might be a good possibility to remind you all that we are still looking for some angels. You could do video angels, which are in high demand right now, or you could just do any other work you would like to. You can do 1 or 2 shifts, that's fine too, and greatly appreciated because we highly require volunteer work for this event. Also, if you brought any beverages in here, it would be awesome if you could take them out with you and put them into the little storage cases that are located all around the building. Trust me, when we are finished, you can do this announcement yourself. Are we good?
Not really.
Okay.
It looks good on the laptop, but
you want to give a quick introduction into the new Ubuntu desktop, because I did not get that at all. Like, yeah, mirror displays, man.
4:3 Folien.
Now we're making progress. All right. Enjoy the talk.
Okay, perfect. Now with slides.
One small announcement, there will be 5 minutes of extra talk in the end.
We'll do that. So just please ignore the yellow bars, but it's not really, no. High-level devices, big complexity. Yes? Yeah, perfect, thank you. Without yellow bars, thank you. Okay, so we already talked about the prerequisites, so now we're going deep into the topic. So first, we need to obtain a firmware. Okay, we will go from non-invasive to invasive, because, okay, the first thing we want to try is getting the firmware without opening the device. So we will first try to download it from a plain binary from the manufacturer. Or maybe somebody else has already extracted a binary and placed it on the internet. You can try to download a boot disk, USB, CD-ROM boot image, whatever the manufacturer provides, and extract it using, for example, WinRAR on Windows, or just mount it on Linux. Search for files named bin, hex, S19, mod, like Motorola, ROM, or RAW. Most times, binary, that means bin, ROM, or RAW files are already real binary files. Non-binary files should be converted to bin files, for example, with converters like hex to bin. Okay, if this doesn't work out, maybe we get an updater from the manufacturer. Normally, there are exe files built for Windows. There are different updater types. First, the self-extracting archives. It might be an installer tool like Install Shield or whatever. It might be an updater, simple exe file without any installation, just containing the image. It might be an updater that is downloading an image. Or it might be some of the others, but being packed with an executable packer like UPX or PE Compact. Let's go a little bit into detail. So, if it is a self-extracting archive, search for signatures like RAR SFX or PK. You can unpack them. For example, if you just rename a PK containing file to .zip, you can unzip it. If it is an installer, like Install Shield, there are special unpackers, but the problem is they are very hard to use. They are extremely version specific, so it might work or might not. So it's the best way to just let it install and search in installed files for a plain image or an updater. If it is an updater just containing the firmware image, we can search the image within the executable using your favorite hex editor. Maybe the updater is writing the data to a file, into a temporary file in most cases, and deleting it after usage. You can use Process Monitor. It's like strace, but on Windows world. And you can take a look what files are written to disk, and you can try to capture it before it's getting deleted. Maybe the updater is just checking your device, so it's just a little downloader, checking your device type, taking a look on the FTP server of the manufacturer, and is downloading an image if there's one available. So, if it is downloading the image to a file, Process Monitor again. If it is just downloading to RAM, okay, you have to go for a debugger, and you have to dump it from memory. If you have a packed updater, which is of course only done to save size, of course. If it is standard UPX, you can just download UPX and you can use UPX-D to unpack it. But sometimes the manufacturers violate the license of UPX and they modify UPX by removing vital file information to make it undepackable. So you would need a special unpacker. Other executable packers are most times designed not to be to make the files not to be uncompressed. So you would need special unpackers too. One challenge that waits for us is that maybe the updaters contain compressed images. They are normally unpacked before the image is written to the device. So we can just watch the process memory of the process and with the debugger, and we dump it. What is a little bit more challenging is when the firmware is sent compressed to the device. So we have to use invasive techniques we will be talking about later. It's a good idea to get a sniffer ready when you're first connecting your device to your PC. Because maybe there's the favorite bloatware coming with the device, wants to update it instantly. What can you do to sniff the transfers? On Windows XP, and I'm sorry, it's really only Windows XP, there's Trace SPTI, a fantastic tool tracing SPTIs, SCSI pass-through interface. So you might think SCSI, I do not have any SCSI devices, but very much communication is done using this protocol on Windows to ID SATA USB devices, especially if they are ATP. On Linux side, you might use Wireshark to trace the communication because Wireshark on Linux can trace and sniff USB. There are various other tools around, like BuzzHound and so on, to watch communication on buses. But the problem is they are normally very expensive. A problem you have if you're trying to just sniff the update transfer and reconstruct the image is that it's like a puzzle. You don't know how to build the image, and maybe you don't know, am I doing it right or not? So, if we do not have a firmware yet, it might get invasive now. We'll search for serial interfaces. Sometimes they are accessible without opening the device, sometimes not. Do we have an embedded Linux system? Yeah, we search for serial console. Maybe we have to use JTAG. There was a very good talk on 2073 about JTAG, serial, flash, and so on. So I've included a link here. So, still no firmware? Get your screwdriver, let's void warranties. We open the device and we search for memory devices on the PCB. If you have a very old device, maybe you will encounter EPROMs or even PROMs 27 something. If it's a little bit newer, you might see EEPROMs and flash 28, 29, 39, 49 something, and the big flash devices and bigger devices with 48 pins, for example, with various other names. But very nice to see is that serial flashes, those 8-pin devices, 25, sometimes 24, are more and more becoming a standard. And they are easy to desolder, they are easy to resolder, and there are very cheap readers and programmers available. But please, even if some say we can do it in system without desoldering the chip, please don't do it. It can lead to very big problems. So, to make it a little bit harder, firmware can be contained in chip internal memories. Like, you can try to use proprietary programming interfaces to read the firmware. Of course, JTAG. Some devices do have bootloaders in a mask ROM. You can try to use them. And if nothing of these approaches succeed, you can try microprobing. There was a talk on last year's Congress about low-cost chip microprobing. I've included a link here. So, just for a matter of completeness, I'm mentioning CPLDs and FPGAs. You know, CPLDs are built up using internal EEPROM. FPGAs, field programmable gate arrays, have internal SRAM and an external serial configuration flash. Some years ago, they were marketed as being reverse engineer proof. Okay, yeah, maybe. There's a talk tomorrow, same time, I think, Saal 2, about taking a closer look at FPGAs. Yeah, congratulations, we've done it. We have our firmware, perfect. So, what's next? Now we have to analyze it. The problem is, what processor is used? We don't know which disassembler to use. So we're searching the web for any data sheets. Can we get any information? Has anybody on the internet already found out what processor is in use? You know, the problem is, in many cases, you won't get the data sheets because the manufacturer says, okay, you buy 1 million a year, 1 million devices a year, and you sign an NDA, you get the data sheets. Okay. So now you have to be really patient because now it gets to trial and error, trying n different disassemblers. You can use specific disassemblers. They are only built for one architecture. You can use a very good tool, the Interactive Disassembler, IDA. There's a freeware version. I've included a link in the link section of this talk. But the freeware only has a little set of architectures. And if you want the full set, it's getting very expensive. But there's a new tool that I really like. It's ODA. It's the online disassembler, supporting 30-something architectures, and it's free. You can upload binary files, you can upload code, and you can try different architectures to find out what might be the correct one. And we'll do that now. So I've prepared some binary code. Okay, I know which architecture this has been written for, because I did it. I've put this code to online disassembler. And I've chosen different architectures. And now let's take a look what the disassembly looks like. So let's first start with former Hitachi, now Renesas H8S. I hope you can read it. Take some time and please raise your hand if you think that this is valid disassembly and we have found our architecture. Okay, I see one hand. Okay, I have to disappoint you, I'm sorry. It's not valid disassembly. We can see it in the second line. The disassembler was not able to disassemble the data, and it's just an undefined instruction. There are several dot words in the code. Yeah, okay, it's not H8S. Let's try MIPS. Again, take some time and raise your hand if you think that this is valid. Okay, again. Okay, it's invalid too. We can see it again in the second line because there's a D word that was not disassembled. Okay, what about Panasonic MN103 family? The same hand again. Oh, I see another hand, okay. Okay, several hands now. Yeah, okay, thank you. So the problem is it's not valid. I have to disappoint you. The problem is, in this case, it looks really good. And you have to dig deeper. You will have to look at, are our subroutines correct? Do they make sense? Are there subroutine calls at all, and so on? And you will see, something is strange. Okay, last try. What about Texas Instruments MSP430? And again, please raise your hands. Okay. Yeah, this time it is MSP430. Okay, we have found our architecture, perfect, Eureka, bingo, we have it. But what's next? The offset in the file, in the firmware file we loaded, is often not the offset in address space. So this is no real problem when we use, when the architecture is using relative addressing. Relative addressing means we have a register content, and whatever we want to access is based on some register's content, location-independent code. But we have a big problem when absolute addressing is being used. And even architectures supporting relative addressing do have some absolute addressing still somewhere on some axis. We would not know where's the entry point, where should we start? Interrupt vectors might be decoded completely wrong. Subroutine calls do not make any sense. They go to outside of our firmware, for example, or in the middle of instructions. So the load offset has to be found out. I'll now show a method I call call distance search. We will select closely located subroutine addresses, and we have to decide either to use preceding return instructions in front of the subroutine or the start of the function entry sequence. We build a search string containing wildcards, and then we search. Okay, now we do that together. I've prepared an example. This is 8051 code. The 8051 core is very old. It's an 8-bit controller, but it's still widely used in the field because it is cheap as dirt, and you can implement it wherever you want. In the left column, we see the addresses of our example, from 0 to 13 hex. We see 4 subroutines, while the first being the root subroutine, calling the other 3 subroutines. And we can see that the first call to 100 is outside of our example. We do not have a 100 hex in this example. So what we do is we are taking the 3 subroutine addresses and sort them. So we're getting 100, 103, and 107. We built a difference to figure out the length of the subroutines. So we get 3 bytes and 4 bytes. Now we take a look how subroutines are built in this specific architecture. On x86, you will mostly find, not on the 64-bit platforms, but the 32-bit platforms and 16-bit platforms, you will find a stack frame entry sequence in every function, like push BP or push EBP, 5.5. So you can trigger on that one. On 8051, it's not possible. Take a look at address A, it's E0. Take a look at address D, it's 44. And 11.7b, they are not equal. It does not help. So we take a look at the preceding returns. And yes, there are returns in front of every subroutine. So we take the 22 as our anchor. So our search string will look like this. We start with a 22. We have a subroutine with a length of 3 bytes. So we have 22, 2 wildcards, and again a return. The second part of the search string encodes the second subroutine with 4 bytes. So we have wildcard, 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 and again a return. Okay, in this example, in this simple example, we get only one hit. Perfect. We get a hit at address 9. But we do not want the address of the return. We want the address of the subroutine. So we are not using the 9, we are using the A. What we do is we take the original destination address 100, we subtract A, and we get the base address of our code example, which is F6. If we apply this newly found out load offset to the code, and we adjust the offset, starting now at F6 on the left column, we see that all 3 subroutines now match. The call to 100, the call to 107, and the call to 103. Okay. I think this was hard. So let's repeat what we have already done. So we have obtained our image. We have successfully found out the processor architecture. We have found a disassembler to disassemble the firmware. And we hopefully have now found out the original load offset. So what's next? Maybe the question arises, is there any additional firmware in this device? I see jumps and calls outside of our firmware we already know, although we have adjusted the load offset. Is it maybe chip internal? You can see it in figure. Maybe we have only firmware part A and it is using a library in maybe chip internal and firmware part B. So we will have to see what you can do using a modification of the firmware. Now having done that, we can start with normal reverse engineering of the code. We search for strings, we search for references to the strings, but as we are in a very low-end embedded system, maybe we can search for very specialized data reference and operands. Search for USB descriptor fields you have extracted with LSUSB. Take a look for USB magics like USB-C and USB-S. You know, these 2 D words are used in the USB communication. Take a look for IDE, SATA, ATP ID strings saying I'm OCZ SSD device, for example. Maybe when you've sniffed the communication with the device, you've already found out some typically communicated data blocks. You can try to find them. And last but not least, maybe your device provides some error codes, and you can either search for strings or for operands in the opcodes. It's very interesting to find hidden firmware update sequences, of course, because they would allow non-invasive modifications. For example, search for chip erase and programming commands. You can take the appropriate commands from the datasheet if there is any external memory device available. Okay, we've done it, we've analyzed it, and we've learned a lot about the device. So now we are going to modify it. And first thing we have to think about is, if we are going to modify the firmware, we have to prepare to break our device. You know, manufacturers implement several integrity checks. And why do they do that? They do it because firmware is most times stored to flash, and flash is prone to aging, especially if heat is involved. So they do checksums. There are software-based checksum calculations, CRC, for example. There are even hardware-based checksum calculations where some hardware peripheral will do the job for us. So what you see in the code is maybe a start offset, maybe an end offset, and if you are lucky, the polynomial. It might be hard-coded to the peripheral too, so you won't see anything. It can be a combination of both, being done, for example, only on startup or cyclically in the background. So what we have to do if we modify the firmware is either correct those checksums, or we have to patch the checksum algorithms not to trigger. What are the goals of our modification? Of course, we already heard it in the motivation section. We are about to correct errors. And maybe the errors are contained in another part of firmware we are not having right now. So maybe we have to dump additional memory regions. And that's what they did in the Cisco Voice over IP hack. They tried to find a memcopy routine and used it. If you don't find a memcopy routine, maybe you can implement your own. Why not? You could, for example, dump code from other memory regions to output buffers. Or if you have space in an external memory device, why not programming it to the device and reading it from the device? It can be very interesting to gather more device internal information. For example, doing a RAM dump, because you know, during static analysis, you always wonder what might be in RAM and on this and that address. Now, as we have modified the firmware, we can inject it back to the device. For example, using the original updater. It might contain the next checksum check, who knows? We can try to reprogram it to the external memory device if available, or to the processor. And this might be done using a serial interface, either JTAG or proprietary. So, that's it. Thank you very much.
If you have any questions, please do line up at the room microphones. There are 4 here. Are there any questions? Microphone 1, please.
Not a question, but a tip. If you need some binary dumps or some leftover files on Windows, you can deny the delete write. So the installer or the updated program isn't able to delete its temporary files.
Yeah,
so they are left over after reprogramming the device.
Do you have a tip what to use in that case?
Sorry?
Do you have a tip what to use in that case? Is there a special tool?
It's not necessary. Windows has the functionality built in.
Okay.
In the I don't know the word.
Okay.
But you are able to revoke writes completely for a directory.
Okay.
There's a special write, deleting, and so on.
Okay, thank you.
Are there any more questions? Doesn't look like it. Please give a warm round of applause to our speaker, Stefan Wittmann.
Oh, on 2.
There is one more question. No.
Okay.
Also, if you're leaving, please do take your